Recording in progress.
All right, guys, we're going to continue. Okay, so I ran the code. You can see the loss function went down to 0.24. And if we take a look over here, our R square is 0.34. Our last one had been 0.27 and 0.29, so it did go up a little bit, all right, with a deep neural network, basically. Any questions? So this is the result of running our deep neural network in the previous architecture. All right, before we conclude this example, I'm going to do one last one, which is now you crafting your own types of architecture. So this is going to be what is called a linear plus nonlinear neural network. So basically two neural networks that you're going to try to combine together. All right, so I'll give you the intuition for that one. So actually for this one, I'll start with the diagram before. All right, and then I will discuss the code. So let's go to the whiteboard. Sorry. Go to the whiteboard. Can I give you the intuition of the things that you can do with neural nets? Okay, so we're there. Okay, so this one, basically the way that it is, it's actually two neural networks that will kind of work together to produce a result. Okay, so think of it as that and that, right? So the linear part is like this. 1, and this is 11. 1, 2, ... 11. And this is the same thing. 1, 2, 3, ... So 11. So basically your vector would go in here and here, right? And then this one is still going to produce 1. And I believe the hidden layer was 14. As I just find it. So 1, 2, ... 1. And then at the end, these two outputs just get added together. So it will be, maybe I should have done. Let's call this one F1. And then this one F2. So that the final result is F1 plus F2. So that's a new neural network that I'm defining here. And why is this? The intuition would be that you're using a linear model, maybe, and then just adding a little bit of nonlinearity to it, right? I mean, this is, you can try different variants of this, but this is just an explanation. So this is F1, F2, you add them. What's important is that this value R is what is always going to be compared to the real value, right? And try to minimize. So the weights of this and this are going to be changed based on this operation. Do you see that? So maybe it's going to determine that this is the most important thing. And so it's going to update these weights to be really good. And then this is just going to improve the results a little bit. So what it does, honestly, I don't know. That's up to the neural network to figure it out. But what's important is you can build architectures like this, combining different neural nets. Okay. Does this make sense, guys? Yeah. Do you have a question? Just add them. Just add them. I'm not saying this is great, or I'm not saying it's bad. I'm just showing you that you can do this and take other approaches as well. If you think about it, you might question this, but transformers do this. Transformers, ChatGPT, all that stuff, they create a tensor that is the embeddings, and they create another tensor that is the positional encoding. And they're basically the exact same thing. N by 40 by 728. And the other one is N by 40 by 728. And so you just add them. And then this is what continues into the rest of the architecture. This guy over here. Does that make sense? So you could, in theory, in an LLM, create your own N by 40 by 718 out of whatever logic. And as long as if this is valuable, believe me, the neural network's going to want to use it. Do you see what I'm saying? So this is kind of the same idea here, only this is just two values. When we look at the transformer, try to remember this, because I will definitely point it out to you guys when we look at a GPT, because this is how they work effectively. Got it? All right. So we built this architecture in the board. Now let's go and take a look at it in the code itself. All right, so you can see linear plus nonlinear, F1 plus F2. So what we do, in the constructor, X means and X deviations come in. We're doing this all day. Then basically we create one self F1 linear, so 11 to 1. That's that linear 1, F1, right? And then I create another set F2, which also takes in as input 11, transforms it to 14, has a sigmoid in there, then 14 back to 1. And so now, in the instantiation of the forward function, I take in my X, goes into this and becomes F1. And then this one, F2 linear, takes in X, notice the original X, right? Nothing to do with this model, just completely the original, produces F2. That F2 goes through the activation, and then that goes through F2, the other one, and now you have F1 and F2, and then I just add them together to produce Y pren. Remember that the weights, that the intuition that you should see here is that the weights are going to try to produce the best result. And F1 weights are going to be changed, F2 weights are going to be changed until it produces the best thing. So it's taking the combination of both to do that. And as I said, GPTs do this exactly, where you have something called a positional encoding, which is much straight. And I mean, both of them are actually simple. This is just the embedding of the words, and this is just the embedding of the position, basically. But you add the two tensors, they both need to have the exact same dimension, and then that goes through the neural net. Got it? All right, so we did that one. So that's going to be called linear plus nonlinear net. So let's run that one. I'm not saying it'll be better. Can't remember, honestly. But just to show you. Okay, and now we can proceed to train it. Oh, okay.
Harvard method F1 is linear 1.
Did I miss one? Linear one, right? Thank you. Yep, sorry. All right, so there we go. It's training. So let's let it train for a little while. I don't know which one will be the best, but we've tried 4 different architectures. Okay, this kind of concludes the linear regression part of this. Right now, I'm going to use the same data set, but I'm just going to contrast if it was a classification, right? So I'm gonna use, we're gonna basically make it into a classifier now instead of a regression thing. So remember, it's still gonna be the 11 inputs, but now it's gonna try to classify it into a rating, like a 2 or a 5, or whatever it is, right? So this is more of a regression problem, not really a classification problem. I'm only doing this to show, within the same data set, what are the tweaks that we have to do to a linear regression to make it into a classification, okay? But it's technically not a classification. Got it? What was more appropriate as a classification was what we saw last week with the iris data set, right? Because here, one problem with this is that in the rating system, there is meaning in the sense that 3 might be more than a 2, and a 7 might be more than a 3 because it's a higher rating. Whereas in the iris, a setosa is not more than a versicolor, for instance. Right? Any questions so far? All right, so while it's doing this, remember, look for a homework assignment this week, although it's not going to be due until a week after the exam. I remind you, the exam is next week, exam 1. It'll be during the second half of class. I'll probably do some lecture slides in the first half. I just summarize a lot of these topics more in like a theoretical kind of a thing, okay? And then that's kind of the conclusion of the first third of the class, which is like the basics of this. We've done deep learning on 2 data sets, and we'll start looking at the second third of the class, which we'll start looking at more classification with image processing, and that usually involves introducing convolutional neural networks. So we'll take a look. Okay. Right, so you can see it's much slower, right? Notice that hopefully because there's more layers in there, more weights to process, etc. So as these models get bigger, they get slower. This is why I was able to get you a Scholar. I just haven't set it up yet, but at some point you'll get that. Yeah. Questions while we wait? All right, well, I guess while it's doing this, we can start downloading the Jupyter for the other problem. All right, so I'm going to do the exact same thing. I'm going to go to the GitHub, second edition, chapter 4. And now it's going to be classification, deep learning algorithm, PyTorch wine. So I'm going to click on that. The code will be pretty similar, but it's going to have obviously some differences in the architecture, etc. So I'm going to hit download. Okay, so download it. And then I'm going to go to downloads. Downloads. Classification wine. Go copy. Go to desktop. Okay, and we have our Jupyter there. Okay, so wow, it's still going. All right, so in the interest of time, you guys know that it'll finish. I, do this at home, right? Look at it. I don't remember if the scores are going to be better than the deep learning algorithm anyway, maybe. All right, but it should be the same process, right? And then you'll get an R squared. All right, so I'll stop this one. This is going to take a while. All right, and I'm going to go ahead and get started with the other one. Okay, so I'm going to go back to here. The Jupyter should be in there now. I'm also going to stop this because it's running. Or not. Didn't I add it in? Oh, maybe I didn't move it into the. Okay, so yeah, wine quality. Okay. Now it's there. Okay, so classification with wine, right? So we're gonna do, as I said, the same problem, but now let's say that you were gonna treat it as a classification problem. I'll repeat, wine quality is not really a classification data set, it's more of a regression data set. But I'm only doing this to show the differences, the subtle differences between regression and classification. All right, so let's go ahead and start this Jupyter. Some of it will be very similar. All right, so let's go ahead and hit the kernel here, clear outputs, restart. All right, so it should be clear now. We'll try it one more time. Okay. All right. So basically, you're set the idea if you want to use a classification on the wine quality data set, then how would you go about it, right? How would you go about it? And you can compare to the regression one and see what is different. So a lot of it, though, will be very similar. Probably like 80% of it is literally the same code. So let's go ahead and run it. Start with libraries. Our libraries are the same ones. Wait for the dark dot to write inside. Okay, I'm gonna do the next cell. Okay. Scalar and metrics. So this time, notice that we're going to invoke confusion matrix, precision, recall. These are the metrics that we use in the iris data set. These are the classification type of metrics that we're going to use now. I'm not going to use XGBoost. We're not going to deploy to the web. Okay. All right, the parameters, notice, batch size 32, it just changed it. Learning rate 0.01, kind of the default. Number of epochs, 1,000. So that tells you that this might need a little bit more training. Epsilon for the normalization process. All right, so let's go ahead and run these. Notice the reading the data is pretty much the same function as before. We do it with pandas. Okay. There's our data. It looks exactly the same. Because it's a classification problem, I'm going to have to modify that quite a bit, right? So that's where a lot of the processing will need to happen in that last column. And I'll tell you why. But right now it's 4,898 rows times 12 columns. We look at the header list, same. We had talked about this already, correlation coefficient, kind of just to see the relationship between the variables and things like that. Okay. All of this we've discussed. From pandas, I convert it to NumPy. Can visualize it as a NumPy, print the shapes, pretty much 4,898 times 12. Same thing as before, right? The labels, in this case, now they're called labels, not regression values. They're going to be in the last column. And so we're going to slice out from the data our X and Y. You can take a look at X dot shape, right? And Y dot shape. Oops. Okay. So here we have 4,898.11 and 4,898.1. So now we have to think about dealing with those labels, basically. So that's this next part. So I want to know actually what labels I have in here, first of all, right? Now, you know that in theory, it's a rating scale from 0 to 10. But do I actually have values for every single one of those 10 categories, right? So that's the first question. So I'm going to look at convert the y's into integer, basically. And I'm going to use NP unique just to see the set of values that I have in there. So as you can see, I have 3, 4, 5, 6, 7, 8, and 9 in there. I don't seem to have 1 and 2 in there. Okay, so I actually don't have 10 classes in there. I have 3, 7, right? About 7 classes, it seems. So that's something very important, especially because it's missing classes 0, 1, and 2. Torch does not like missing values in a sequence of numbers that are classes, right? So we're going to need to do a mapping of these such that 3 is 1, 4 is 2, 5 is 3, and so on. Does that make sense? Right, so that's one thing we have to do. There are 7 classes. I'm also going to plot the histogram here just to kind of corroborate this a little bit more. And you can see I have values for 3, very few, by the way. Very few values for 9. The dominant is 6. So this also brings in the fact that this is not like the data set of Iris. If you remember, with Iris, what did you have? You had a balanced data set. You had 3 classes where each class had the same number of samples. Now I have 7 classes where 1 class or 3 classes dominate and the other 4 are very low. So this is a highly imbalanced data set. So this is another reason why I like to use Iris, because it also helps me to show this issue. This is a hard problem. Okay, does that make sense, guys? When you measure performance, you should definitely look at the performance on a per class basis. Now, there's some argument to be made that maybe you should just drop classes 9 and 3 also. Okay, so and you should just maybe focus on these 3 or something like that. These are decisions that you'll have to make. In my case, I think I'm just going to use all classes as is. Okay, any questions about that? All right, so let's go ahead and do that. So, again, I'm printing the shapes, same as before. I'm going to do the poor man's, splitting, and which allows me to do tenfold cross-validation. So now I have the shapes there, right? Look at the data type, float 64, and the y's are in 32, so that should be fine. So I change only the floats from float 64 to float 32. And then I changed all the NumPy arrays back into Torch. Okay, so now they are Torch tensors, which that's what PyTorch needs in our particular setup. Does that make sense? This is very similar to what we did before. Does the normalization need to happen? Yes, it needs to happen because that related to the inputs, not to the outputs, right? So the inputs, same situation. So we're going to normalize, standardize them. In this case, we calculate the means and the standard deviations exactly as we did before. Okay, so we have them there. So I'm going to skip printing the shapes, given that we had done that already. And then this is where now, to create the data loaders, we have to consider the fact that we have classes instead of regression values. Okay, so if you notice, I'm going to go ahead here. We have 3,918 samples in X. Now we need to map our, we're going to need to map our values or Ys into these classes, right? So here, if you notice, I'm going to create a dictionary. Basically, one is called, or something called the label map and a reverse label map. The reverse label map is just so that when we have the results, we can like predict it back out to whatever it was. So if you notice, all that this is going to do, this is a dictionary. So if the key is 3, it assigns a 0 to it. If the key is 4, it assigns a 1, and so on. Notice that the thing that's important is that now the values go from 0 to 1 to 2 to 3 to 4 to 5 to 6. Because Torch will not like missing values. It'll give you an error in the data loader, actually. Does that make sense? Okay. And you can see the reverse map just does the opposite. So if it's a 0, it's going to return that it was a 3. If it was a 1, that it was a 4, and so on. Okay? So that's done here. So we have the maps. Okay? And then now we create the lists that are going to be fed into the data loader. So as you can see here, we're going to have wine train list and wine test list. Okay. So basically we just iterate for I in range of all the samples, right? And what do? We grab the sample, Y train TRI, and then we grab the corresponding label, which is wine Y train TRI dot item. That's going to give us, let's say, a 4 that goes into the label map, right? And if it's a 4, it's going to return a 1. And that's the class that gets assigned. Does that make sense, guys? Pretty simple, right? Pretty straightforward. And as I said, that's just so that Torch doesn't complain or the data loader doesn't complain. We do the same with the test lists, pretty much for I in range, X test shape, right? All the samples. We grab X test TRI. We also grab Y test TRI item, plug it into the label map. If it's a 2, let's say, did we have a 2? No, if it's a 6, then it's going to plug in a 3 in there. All right. And that's basically it. So once I do this, I run it. So you can see that. Now, if I want to look at Y train list, you can see basically the vectors are in there. Okay. And the corresponding label. Okay. The tuple basically of feature vector of 11 to label 4, 3, 2, and so on. And then once that's done, I can, just like we did last week, the nice thing about the data loaders is you can just give it this list in this particular format, tell it the batch size, which apparently is 32, and we tell it that we want the data to be shuffled. So it'll just shuffle it for us every epoch. Okay, and that's really handy. Makes, it reduces the amount of code you have to write or worry about. Okay, and then we know there's 980. Okay, and then we're going to repeat the same for the test set. So we're going to create a data loader for test. wine test list, batch size in this case, it's just going to be the whole data set. Because it's the test set, there's no need to like feed the model, the test set in batches, right? So we can just give it the whole thing, as long as we have enough memory. But we do this in the training, but not in the testing, okay? So basically one time we'll give it the data, right? And that's it. They're both created. So now we can proceed to create our architectures for our neural networks, right? So notice here I have an MLP, a DLNet, and that's it. Okay, so I'm just going to have two architectures, and now we're going to think about how we're going to do this. So notice we gave the data initially. This is something important to remember. We gave the data as the class is 4, or we set the class as 0 or the class is 1. We're just providing one integer, right? Keep that in mind. That's really important. But we're giving that to data loader, which has some capabilities to help us out, right? So that's how the data has been provided. Now we go to the neural network. And for the classifier, we're just going to specify, you know, just like before, right? We do a class, MLP. It'll have the init function for the constructor and then the forward function to build the architecture, okay? That's it. So this still inherits NN module. We still use X means and X deviations, and that gets fed into these variables because remember, that's the normalization of the 11 features. That hasn't changed. And then now notice our architecture changes a little bit here. So we create a linear that will receive inputs of size 11 and map them to vectors of size 5. So that's the transformation that's happening from the input layer to the hidden layer. I'll draw this in a second. Notice that then we have a ReLU activation. Then we have a next layer, layer 2, that goes from 5 to 7. Why 7 this time? That's the last layer of the output because we have 7 classes. So that's one thing that we have to do when we do classification is based on the number of classes we have, you know, that number of output neurons. Do you guys see the little subtle difference? Very important. Then I have something called the softmax, which this time I do have to define what this softmax does, but it's pretty straightforward. Okay, and it's also in the notes that I provided, so hopefully you read through that. And then we have the dropout, okay? So now that we've instantiated those things, we can go ahead and proceed to build the architecture. So I have my defined forward function. Notice that I give it X as input, okay? I can normalize it by doing this if I want to. Notice it's commented out currently, but you guys know how to process that. Then I have X goes through the first linear, 11 goes in, 5 comes out. Those vectors of 5 then go through the activation, which is a ReLU. Remember, I just said it takes the values. Any negative becomes a 0, and positives are allowed through as they are. Then that vector of size 5 goes into linear 2, and that transforms into a vector of size 7. And our classes are, there we have 7 classes. So basically, you're comparing a vector of 7 to 7, basically. And then we have to wrap the softmax function around that vector. And that basically is something I still need to describe, but that's pretty important. It only happens on the last layer. You can see that here, activation 2, where activation 2 is this softmax, basically. Okay, everyone with me? All right, so that's the and then the output of that, which is a vector of size 7, is what comes out of the neural network, okay? All right, so now that we've talked about this one, let's go to the whiteboard and let's recreate this. And the whiteboard, remind me of the values. So it's 11 to 5, 5 to 7, right? So let's take a look at it. Okay, so I'm going to draw this now. So the input is 11. I have a hidden layer, hidden one of size 5, hidden one. This is the input. So, 1, 2, 3, 4, 5. 1, 2, 3, dot, 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 11. And then I have one layer with 7. Okay, and that's the output layer. That's your neural network for the MLP. Does that make sense? We wrap a ReLU here. Okay. And then one of the new things is that here we have to wrap a softmax. What does softmax do? I won't use 7 because that's too many things for me to write, but I'll imagine it was only 3. So the vector of 3, let's say, came out to 0.4, 0.6, 0.3, right? You see that? This could happen without a softmax. I would still say 0.6 is the highest value, so it would be this class, right? Assuming these classes are 0, 1, and 2, then it would be class 1, and that's the class that I would predict. Do you see that? But this doesn't intuitively match our real data. Why? Because our real data will be annotated. We would have 3 things, such as Setosa, Virginica, and versicolor. We know what they are, right? We know that this sample is one of the 3. So our annotation would actually be 1, 0, 0. Do you see that? Just you're sure. But this model predicts 0.4, 0.6, 0.3. There's one very fundamental difference here. All of our annotations will be like this. Only one of them will be 1 and the rest will be 0. So when you take this as a probability, they always add up to 1. 0 plus 1 plus 0, 1. If it was 0, 0, 1, 1. If it was 1, 0, 0, 1. It's not going to be 1, 1, 0. Then you've done a bad annotation. It's a different kind of problem, not what we're doing here. Do you see what I'm saying? So intuitively or theoretically or whatever, you can say that this adds up to 1. That data distribution has that property. So we should make this one have that same property, that it adds up to 1. Do you guys understand what I'm saying? That's a desirable thing, that it has that property, that the value should add up to 1. So there's a function called a softmax that can do that for us. What that means is, staying with our example of this, 0.4, 0.6, 0.3, which does not add up to 1. This is 1.3, right? It does not match this distribution. So then what you do is you run these vectors through this function called softmax. And the property of softmax is that it's gonna, just like sigmoid and all those other ReLU, map to a scale. This will do the same, but it'll produce a new set of values which now should add up to 1. So for instance, here I'm going to say this is 0.5, this would be 0.3, and this is 0.2. So when you add these, they will add up to 1. It'll force the values to do this. And, you can still see that 0.6 is still the dominant one, right? So it's still class 1, but this is just better. And it has been found that this will work better in your prediction. You see, that's the key insight. We wouldn't do softmax just for theoretical purposes, right? We do it because ultimately it does do better. But it's because this intuitively has that property itself. Make sense, guys? So this is the one function that we've added. Keep in mind the vector here, the output has 7, right? If I didn't write it, it's 7 neurons now, not just 1 like in the regression. So we have to consider that. All right, so, well, all right, so we built the neural net. Now let's go ahead and continue. Okay, so we're back. So we built the MLP net as exactly. I'm gonna run that one. I'm gonna skip the DL net for now, just like we did before. Now we're back at the train loop. Look how quickly we're back at the where we were. And let's take a look at it. So I'm gonna remove this because this is just me printing out shapes and things. All right. So now I have the training loop, the same parameters, 2 for loops for epoch and epochs. That's we give it the same data set, shuffle 1,000 times. We're going to, out of the train DL, take a batch of 32 by 11 and a batch of 32 by 1 currently, right? We haven't really made it into 32 by 7, for instance. In the past, you used to have to do that. But the beauty of PyTorch and things like that is that because it's in a data loader and everything else, it just knows what to do. As long as I made that little thing of starting at 0, 1, 2, 3 to 7, then it knows exactly what to do, okay? So notice that I give it XB, but I wasn't really needing to notice this, right? My architecture was 11 by 14, I think it was, to 7, right? Of the MLP. Never did I go make a, I never made those, I never one-hot encoded the labels. The labels were still 3, 7, whatever it was. So let's take a look here then. I'm going to do print YB, right? Which is the YB shape. I'm just going to do an input there. But take a look at that shape. When XB goes into the model is going to predict Y pred. We want to look at that too. What does that Y pred look like? Print Y pred dot shape. Okay. And then that goes into the loss function Y pred and YB. What is the shape of YB? So, as it turns out, the losses can help you also, right? So the loss function that we're going to use, sometimes those loss functions, if you read the definition of it, it says it can take something as a vector and something else as an integer and just figure out the one-hot encoding. So you don't, so this is what, I believe this code will work. So obviously I have the right definitions of them, but I want to print the shapes just to kind of get a sense of how it is. And then it goes into the loss. The loss obviously is the same thing as before. We are trying to minimize the error between, the predicted and the real. And we take these steps that we'll describe a little bit later. Okay. And I'll probably have a syntax error here. Parentheses. All right, now here I'm doing the MLP net, right? Similar to before, same optim, just the same thing as before. This is really important. Notice that instead of using the MSE loss function, which was for a regression type of a problem, now I'm using the cross entropy for a classification. There are basically 2 loss functions in all of deep learning. There are several variants of these with different names and things like that. But in general, there's MSE for regression, cross entropy for classification. Okay. So in general, this is what you're going to have. Any questions on that? All right. So for classification now, this is definitely different. This is actually quite a bit. It's in the notes that I provided to you. If you've started to read through that, there's a definition of this. And then we invoke the training function over here. So let's go ahead and run this. Oh, and here it says something, which is actually, it gets to at the heart of what I was printing. It says the Y test data can be integers and does not to be one-hot encoded with this function. So that's the definition of this, this loss, basically. All right, so let's go ahead and run it. So it's running now. Okay, so it only printed one thing. That's great. I think as I put the input, yeah, way too early. Should be here. Okay, all right, let's redo this. All right, here we go. So torch 32, 32.7, 32. Do you guys see that? So what does that tell you? It tells you what is 32, the first one, right? So Y shape is 32, 32 by 1, basically, right? There's 32 samples, but the class is only 3 or 7 or 5. Do you get what I'm saying? Not the one-hot encoded version of it. Yeah? Whereas what comes out of the model is the second thing I'm printing, YPred, right? So if you look at YPred shape, what is it? 32 by 7. It produces vectors of 7. You guys understand? So now it needs to match 32 by 7 to this one, 32. What is that one? That is YB. Okay? So let's go to the whiteboard to kind of visualize this one. This used to be way harder before or way easier, depending on how you want to think about it. But PyTorch does a lot of the heavy lifting for you because this is going to be the use case. The labels are usually going to be integers. What comes out of the network is going to be one-hot encoded. So you were always left with making the original labels. You'd have to do that one-hot encoding. And somebody just said, why don't we make a loss that takes what comes out of the network as one-hot encoded and the rest the integer, and then it does it inside. You see what I'm saying? So, but what this is saying is, instead of 32, I'm just going to use like 4. So 0, 1, 2, 3. This is 7. So effectively, it's a vector with 7 values, right? It's telling you which class it is. Maybe this class is 1. You see that? And then you would have to compare it. So this would be YPred, and this would be YB. So in theory, you would want this to also be like that, right? 7. But if you notice in our example, it's actually just 1. Where the label here, let's see, 0, 1, 2, right? So this 0, 1, 2, so this would be 2. You guys see that? And this is what goes into the loss function. So the loss function is fine with accepting this for the real and this for the pred, no problem. Got it? Just read up the definition of cross entropy. You'll see that it says basically that. All right, in case you have any discrepancies, it saves you the step of having to take this guy and one-hot encoding it into this one. Okay, so you don't have to do it. Anyway, That's it. Those are, I mean, nowadays you have Cursor, which basically writes your code for you. So this is kind of, it's even more help than before, right? So anyway, so hopefully that made sense. Okay, so now I'm going to go back. All right. So I'm going to remove all of these because we don't need them anymore. Two print statements, an input, this print statement, this print statement. Okay, and yeah, no, sorry, we had done MLP.NET. Oh, okay. Oh, it's still running, sorry. MLP.NET. We're not using DLNet right now. So again, okay, so we grab the XB data, right? For training, run it through the model. The model predicts. The Y prets are compared to the YBs through this loss. Remember, this is cross entropy. We'll cover this like in the theoretical lecture next week, just in the slides. And then once the loss is calculated, we perform the stochastic gradient descent process, everything that goes with that, and then update the weights basically. Okay, so I'm going to go ahead and do that. Notice that I have MLP.NET in there, Optim, the same thing, cross entropy. So now we can proceed to train. And all right, and there it goes, and it's training. Since this is a classification, remember that we will have to use the performance metrics that we used last week, which are precision, recall, F measure, and the confusion matrix. This will print every 50 epochs, so, and I'm doing 1,000 epochs, I think, which may be pretty slow. Yeah, because it's at, it's taking a while, right? So I'm just going to do 100 instead. And I'll let you guys, when you run this at home, run it with 1,000, okay? Because otherwise it'll just take too long. Eventually, I think in a couple of weeks, I'll start using the Scholar, which I'll have a GPU, so it'll be a little bit faster. All right, let me rerun this for 100. All right. All right, let's let it train. Okay, so basically, as I said, I'm almost done with this example. I'll explain the other architecture as well, but while it's doing this, once we finish this, we're basically done with the basics of deep neural networks, right? So you're all experts now. All right, and then next week, I'll just do some slides, summarize a lot of these topics in theory, then the exam during the second half. You will have a homework assignment due after, and then we will begin the second third of the class, which is more advanced algorithms. Obviously, CNNs is the next one to touch on. So we'll go over that one, and it'll be image classification of black and white and color images. Okay, so that's the next step. So yeah, any questions while it's doing this? So it's only doing 100 iterations, so it should be done in a little bit. Notice that the loss hasn't really gone down that much. All right, it finished. So now This is the same function that I used before, print metrics function, right? So this is what I used last week. Now notice we do for the evaluation, I'm going to do with torch no grad, right? Why is that? Because we don't want torch to adjust the weights when we do this phase. I'm gonna use the test DL, so same thing, X real, Y real. I give X real to the model, and the model now with good weights, it's gonna give me Y pred. Now once I have that, I have my predictions, okay? I have my predictions. So what is this next step? Y pred, torch max, val, and indices. So what's happening there is that we need to find the index of the highest value. So I'm going to go ahead and go to the whiteboard. So the vector is a vector of size 7, right? 7. This is the output. And then it goes through softmax, right? And it's, let's say softmax. And it produces still a vector of size 7, but now with a probability distribution that adds up to 1. So I'm going to imagine that it looks like 0.01, 0.01, 0.01, just keeping it easy for me to not get confused. 0.02, let's say, so that adds up to 0.05, and there's 4, so I need 3 more. 3 more? Yeah, 3 more. So I'm going to say 0.02, 0.03. So that also adds up to 5. So obviously this one is what? 0.9, right? Guys? Yeah. All right. So this is what comes out. So now the max function, what it does is it takes this vector and it's going to return the max value and also the index of the max value. So we know for sure the max value is that. So it's going to return 0.9, but also the index. So in that case, since there's 7, starts at 0, 1, 2, 3, 4, so 5, right? And that's my label. Does that make sense? So for every one of the samples, we need to do that. Okay, that's what the max is for. So now we can switch back to the code. All right, so here we are. We get the vector, then we take max, and then vals and indices, in particular indices. I just mapped it to preds, so it's more intuitive. And then preds and Y real get compared so that we get the confusion matrix, accuracy, precision, recall, all that, just like we did before. Does that make sense? All right, so let's go ahead and do that. And there we go. So I get a confusion matrix. We want the values to be on the diagonal. For this, they're not all in the diagonal. Why? I already told you this because when we looked at the histogram, it was a highly imbalanced data set, a very challenging problem. So it has almost no chance. I mean, if you only give it 3 samples of a class, it's going to have a hard time predicting that class. Do you guys see that? Okay. There's no solution for that except dropping classes, balancing it, things like that. But anyway, so in this case, you should not rely on accuracy. Instead, a better one would be 0.41, but really you should look at on a per class basis, right? And look at the metrics. So here we know that this model does 0.41 F measure. Still, if this is like the thing that I said, whoever gets the highest is the best, and this is the metric you have to look at. So now we're going to repeat the exercise, but for DLNet, okay? Also, keep in mind, instead of giving it 1,000 epochs, I did only give it 100, so I gave it less time to think about this problem, right? So now let's go ahead and run DLNet. Notice it's going to be the exact same thing. right? Only we need to look at this architecture, drill down a little bit into it. So I'll start running it since it takes a while, and then we can go to the function and just describe it, and then we can wrap up with that for today. Oh, why did it? Oh, I reran it, right? Okay. Right, so it's thinking there. So yeah, there we go. So it's doing its thing. So let's go to that function. DLNet, right? So this is a deep neural network with 2 hidden layers. Also, I didn't normal. Oh, this one I did normalize. I think intentionally. This one was not normal. Anyway, so X means and X deviations, same thing as before. Nothing has changed. The architecture here, though, is a little bit different, right? Linears for transformation. So we started 11, mapped it to 15. I'm using a ReLU activation. Then 15 to 9, transformation goes through a ReLU. Then 9 to 7, and 7 is the output, which we have established already, right? And then we do the softmax over here. So you can see X means, X deviations, standardize, X goes into linear 1. So 11 gets the map into 15. 15 comes out here, right? So 32 by 15 or whatever, that goes into a ReLU. Then 15 goes into this one, right? And 9 comes out. So the tensor, maybe it was 32 by 15, now comes out 32 by 9, okay? You created another vector space, if you will, right? And you do that, and then for the final one, 9 into 7, okay? So let's draw this on the whiteboard, and you guys can remind me of the numbers. So I'm gonna hit whiteboard. So, okay, so here we are. So we know the input. We know the input is 11, very good. And we had 2 hidden layers, right? And then the final output should be 7, for sure. What was this one? 15. And then this one? 9 was it? Okay. All right. We normalize the data here. This has an activation, which is ReLU, right? We've already established ReLU is the hockey stick. This one also had an activation, ReLU as well. And the output and the final one is softmax to make sure that it's a probability distribution that adds up to 1. Does that make sense, guys? Everyone with me? And it's fully connected. So that means every neuron is connected to every other neuron, but dropout would drop some connections during the training. Got it? Yeah. All right. Perfect. So that's, I mean, obviously, I didn't do any deeper neural networks, but you probably get the idea. Expect on the exam, I might say, create a neural network with 4 hidden layers or something like that. But it's an extension of this, right? So you should be able to figure it out. And there might be an example in the notes. All right, so that's it. Any questions about that architecture? Pretty clear? Okay. I'm going to close this one. I'm going to go back to sharing the screen. All right, and we were, it finished. Seems to have finished. That was MLP. So 41, F1 measure was 0.41. That's the value that I want to improve upon. It's actually 0.43, so it's worse, right? Now, deep neural networks do need more time, okay? The data is normalized, so, but yeah, that's basically it, okay? As far as, now, as I said, this is a very difficult problem given that it's a highly imbalanced data set, right? And that's it. Any questions? All right, so that kind of concludes this. I'll run it for a few more iterations for those of you that want to say and see the final result. I'll run it for like 400. Otherwise, just do this at home. so here, right? So let's say 400 iterations. Now on the next time, as I said, that we meet, I'll just do slides for the first half, summarize some of these concepts, then the exam. And in 2 weeks, we will pick up with classification with MNIST. So I'll do MNIST with just a deep neural net, just like this one. And then we'll do convolutions, a convolutional neural network, and lead into that topic. All right, guys? All right, yeah, that's it. And like I said, I'll run this, play with it if you'd like. See if you can prove the results. I'll stay for a few minutes if you have any questions. Otherwise, I'll see you a week from today. Caitlin, do you have a question, or are you just giving me the thumbs up?
No, I'm good. Have a good night.
Yeah, good night.